All right. So what we want to do here is, today we're going to apply what's called this Graph Scale-Change Theorem, as opposed to the Translation Change Theorem, where things shifted. So, and we're going to look at all relations, whether they're functions or not, okay? So the first thing we want to look at by warm-up here is that if you multiply a number by 0.8, you can get back to the original number by either multiplying the product by what or dividing the product by what. Multiply the product by 1 over 0.8 to get it back, or dividing by 0.8. Now, by the way, we already said that this here is actually a different number. It's 1.25, but it's easier to see it when you write it as the reciprocal, to see the pattern. Next, if you divide a number by 30, you can get back to the original number by either multiplying the quotient by blank or dividing the quotient by blank. So we have to multiply the quotient by 30, which would be here, or divide it by 1 over 30. Or divide it by 1 over 30. So the point that we're looking at here is about how reciprocals relate to the different functions. So we're going to see that today applied directly. In other words, it's kind of like with one operation, we use one term, but for the other operation, we use the inverse. And that applies directly to when we shifted things left and right. We use the inverse to shift it one way or the other. Multiple choice. When a is not 0, so this is what's called a complex fraction, fraction within a fraction, and you can go fraction within a fraction within a fraction. There's some very beautiful ones that end up looking and simplifying quite beautifully. But let's take a gander here. How do we simplify this? Typical. So notice here that this fraction right here is going to be reciprocated. So in other words, this says x divided by 1 over a. This is another way to write it. And the definition of division is to multiply by the reciprocal. So this now changes to multiply by the reciprocal, a over 1. And clearly that's going to simplify to this one right there. What we're going to work through is continue going through what we did, and now you need to pull out your handy-dandy Desmos. You're going to enter these 3 functions into the fields. So notice that not the parent function, but this is going to be my base function. And notice that I'm going to take that whole function and multiply it by b. And then notice that each of the x's are also going to be divided by a. And you're going to make a slider. So if you forget how to do that, let's go ahead and walk through this using Desmos, and we will do that. So I'm going to start entering things in here. So there's my first function, and continue on adding things here. Now I've added in a b in the very front, and then I added a slider to that. So notice that my red and my blue are coinciding, so they're the exact same. You don't see a difference right now. And now when I add this last one here, it does say add the slider. So again, the orange is on top of the blue, which is on top of the red there. So what we can start to do here is slide things. I'm going to deselect the one of them. So in this case, I'm going to deselect the one with the fractions. And I'm just going to stretch out and see what happens. What happens when I take the b here, and in other words, I'm multiplying the entire function. If I multiply the entire function, what is going to happen to the whole function? So watch the blue as we go. Notice what happens to the blue there.
I don't have the same curves as...
What's nice about Desmos is that you can actually select important points on Desmos, and it'll highlight it for you. So notice on this original parent function, I've selected a few things. And so notice that with the blue, things start to increase, but this helps us to see about something. So for example, if I were to if I were to make b 2. In other words, I doubled the entire function. Notice what happens. Notice the x's are exactly the same, but look, this one goes from 13.12 to 26.16. So that is going to jump up, as we can see, by 2. So continuing on, if I were to triple things, again, the x remains the same, but 13 times 3 is 19. And the same thing holds true for the lower part as well. So I'm going to deselect that right there. And now I'm going to focus on the other one. Now it's your job, of course, from here to figure out what does this one do when I am effectively taking my my x and dividing by some a. When I take my x and divide it by some a, what happens? So run through the slider and make a prediction there. I think I actually want to make a change here. So if you can watch just to see, some of you might be asking the question, Swenson, why are we dividing by a number over here, but multiplying by a number here? And the one thing I want to remind you is that multiplying is division, and division is multiplication. So let me rewrite this one here. Instead of saying y equals b times all this, how do I, what if I were to put b on the other side? If I were to put b on the other side, I would say this. So let me go ahead and just delete that b. And in deleting the b, but putting it to the other side by dividing both sides by b. Dividing both sides by b. Notice what we now get. Oh, I do have a division by b. Y divided by b is this. And this is my x being divided by a. So notice what happens here still. We're still going to get that effect of the b shifting around. And as I double the b, or look, I put b at 3, or as close to as I can. B at 3, my x stays the same, but my y value gets tripled because b is 3. So when you ask, oh, why did we divide here, but up here we multiplied? It's actually not true. We did divide on this side. We just happened to have the b move to the other side. So y divided by b, or x divided by a number, and see what happens with those. What do we find out? How does a affect? Notice that a is attached to the x. So this is going to be a stretch that's horizontally. That's horizontal. However, the b, which, like we said earlier, if I divide both sides by b, I'm effectively affecting the y. When I change the y by a number, and that's multiplying, this is going to also be a stretch, but it's going to be the vertical stretch. So let's see. In general, a scale change, so we're stretching it or compressing it or flipping it, as opposed to sliding it like a translation, centered at the origin with the horizontal scale factor of a not being 0, because we can't divide by 0, and the same thing, the vertical scale factor of b not being 0, that maps, what does it map? We start with some xy, and here's how it changes. The x is multiplied by the a, and the b multiplies the y. So, whatever number is dividing a in the function, try that again. Whatever number is dividing the x in the function is what we are multiplying the points by. So it's sort of an inverse relationship. We've actually saw this before with the shifting, and we'll unpack that in a second. So the rule for this can be described as not t.
Don't expect that much from me.
All right, so it's an S, probably for scale, and we say xy gets mapped to in this case, ax, by. When a equals b, so if I multiply both of them by 2 or multiply both of them by 3, then the scale change is called a size change. And we've seen this in geometry already. This is where you talk about similar, for example, similar triangles. That if I have a triangle this size and I double this and I double this, I now have similar triangles. In other words, the same shape but different sizes. So when you multiply both the x and the y by the same, it's a scale change or a size change. So in other words, it keeps the similarity. The same shape but a different size, as opposed to being overly stretched out in one direction. All right, so this is going to look very similar to the previous theorem about the sliding and the translation. So let's see. Given a pre-image graph described by the sentence in x and y, the following two processes yield the same image graph, replacing x by x divided by a and y by y divided by b in the sentence. And let's just unpack what we mean by sentence first. It's the equation. It's the equation. And applying the scale change of ax and by to the pre-image. Of course, starting out with xy going to there. Let's recall with our translation theorem. Remember, if I wanted to move something left or right and I had a function, if I wanted to move something left or right, if I wanted to move it, I would replace this h with something, right? So over here inside the parentheses, this would shift in the h. And depending on what h was, remember we always said opposite. It's the inverse of what we see in the function. So to go from function to point, they're opposite of each other, okay? But the same thing is true over here. If I subtract the y by some number, or effectively adding k to this side, because look, if I add k to both sides, it's adding k over here, or just subtracting k from the y. This here is going to create a shift that is vertical by k, either up or down depending on the value. And over here, this one was horizontal. So it is the opposite of what we see. From the function to the points are opposites based on the function here. So these are like knobs. If I wanted to move the whole function up or down, I just adjust this knob. If I want to move the whole function left or right, I just adjust this knob. Well, we've now just introduced something else. That if I wanted to change and stretch it, I can divide here. Or if I wanted to stretch this one left or right, I can divide there. So we now have 4 knobs effectively, 4 different knobs. This knob is a change, a translation up or down, translation left or right. This one is a stretch up or down, and this one's a stretch left or right. And if we do them all at the same time, then I could make the graph from here and just get much larger and shift it over to a different place. So all of these effectively are working in tandem to do my transformations. All right, so let's take a gander at example number 1. The relation described by x squared plus y squared is equal to 25. And hopefully you notice this is a circle. This is a function, or excuse me, not a function. It's not a function, but it is an equation for a circle. And it's graphed down here. Find the images of points labeled A to F. So here we see F, A, B, C, D, E, and E. Under this rule. Then we're going to graph the image, and lastly, we're going to write the equation. So this is going to highlight the difference between a rule and an equation. With the rule, it's just like you're describing it normally. I have x and I double my x, right? So I stretch it out. My y stays the same. That's effectively what's happening here. When we get to the equation, we have to go inverse of what we see. I'm doubling the x, so I'm going to cut it in half down here. If I were translating it, if I were shifting it left or right, if I went right 2, down here, I would go negative 2 for equation. So from rule to equation, those are inverse. All right, so let's see. All this rule says is I'm going to take each point, double the x, and that's it. So for E here is now going to be, and I'll just write it up here, E prime, because that's the image. E prime doubles just the x, and the y stays as is. So E prime is -6, +4. While we're here, let's go ahead and graph that. -6, +4 is right here. So if we look at the original one here, this is your E, and now E prime is over there. And it feels at first, oh, didn't it just shift this way, 3? And we say, okay, it certainly feels that way, but we're not 100% sure. Am I just going to take this circle and shift it over, so now it's just right here? Or am I going to do some other thing? And of course, since I'm doubling my x, this is going to be a scale change too. So the whole shape is actually going to change shape. All right, so just continuing through, not overly complicated here. Double the 0, so D prime is right here, 0, 5, so it stays the same. Notice that C is at 3, 4, so when we double that, we get 6, 4 right here, so C prime is 6, 4. My A originally is 5, 0, so my A prime is 10, 0. In case you're not remembering what I'm saying, A is the preimage, and A prime, and that's an apostrophe there. And we just say A prime, and that means the image of A. And we could go further to say A double prime, A triple prime. That's if the image gets an image as well. So if there's a double translation or a double transformation of sorts. All right, so finishing up here. So we do see, notice that this is becoming elongated here. It's becoming elongated. And lastly, F goes from 4, -3 to 8, -3 there. So F prime is 8, -3. Now, when we are sketching this, I'm probably going to put in a couple extra points, like this point here is going to get translated, and this one is going to get, not translated, but scale change. So it moves over there, doubles over, and this one doubles to here. So now I've got points that I can work with. So as I make it work, it might take some erasing to get it correct. And it's not a UFO, so don't make it like a hard and fast vertex there, because it comes around like so. So we look like, looks like we've made an eyeball, but all we've done here is effectively grabbed both of these edges right here and stretched it out to here. Like I said, we've just taken these guys and stretched them out to here, and now we no longer have a circle, we have an oval situation. Now it's asking us to make the equation. So remember, the rule is a simply, if I want to stretch it twice as large, the rule just says times 2. Now the equation says I need to inverse that. So instead of saying doubling it, I'm going to cut it in half. So this is what my equation will look like. Notice I only want to change the x. So instead of multiplying by 2 on this x, I'm going to divide by 2. And that's it. So the equation here is going to look like this. X over 2 squared.
Wait, where are you writing this?
Now the y stays exactly as is, and everything else does as well. So let's summarize here. The rule describes what happens to like a point. The x gets doubled, the y stays the same. So, but the equation describes what happens to like the whole shape at the same time, and we always do the inverse. So if I wanted to increase the y by double, the x by double, so I stretch it out, then I divide here by 2. But if I also wanted to shift the whole thing up 2, I could minus 2 inside there. And so this whole thing would simply be, instead of being here, I would just move it up to there. So rule versus equation, that's a huge difference there. Take a moment here to consider what is happening before we even do any sketching, and also note that the scale on the x is different than the scale on the y down here. But talk real quick with your neighbor. What's the parent function look like? And number 2, what's happening to that parent function based on this equation, not rule, equation. So on this one, this is the equation. This is the sentence. So we have to think opposite/inverse of what we see. So in this case, y is my vertical, and because I'm dividing by 4, I am going to stretch by 4. So it's going to, as if I'm going to grab the function and yank it up. Now, what's this one say over here? Instead of stretching by 4, I'm going to compress here. I'm going to push it together by factor of 1/6. Of 1/6. What? Where did that come from? It's because it's inverse. Remember that 6 times x is the same as x divided by 1/6. Ugly to see because of this complex fraction here. But essentially what we're doing is dividing by 1/6. So this is how I'm quote unquote stretching it. Now, because of the 1/6, I'm going to compress it together. So your parent function, which we know to begin with, looks like this when all the scales are equal. Here, the scales are not equal, folks, so don't get over crazy on this. The scales here, I'm counting by 5s. 5, 10, 15, 20. This one, I'm counting by 1s. So that means my scale is going to be, my parent function does this. It looks stretched out because of the scale change on the y. So this is the parent function, whether we like it or not. This is what the original function looks like. So how do we stretch things? We're going to do 2 things at once. We're going to squash it in by 6, and we're going to stretch it up by 4. So if we look at this, because the function up here divides by 4, the point is going to multiply by 4. So let's just start with this one here, which is 5, 5. That means this guy right here is going to multiply by 4 to be 20. Okay. Now what about the x? Good. So I'm going to take the x here and divide by 6. So this one becomes 5/6, which is, again, you're going to be a little bit hard to graph that because you have to estimate a little bit. But 5/6 so is just about, here's 1, so here's 5/6, and that's all the way up to 20 right there. And the other one is over here, negative. So the function does 2 things. It gets compressed and stretched at the same time to look like this. On page 3 that you picked up today, let's graph this function. Notice we don't have an actual an equation for the function. We just call it f of x. Y is f of x. That's it. We've got some function here. This is the thing it does. It bounces around like so. So we have to interpret what's happening here. We have to interpret what's happening here and then apply it. So if we look at this first thing right here, this is a vertical stretch by 3. Vertical stretch by a factor of 3. So this is horizontal. And because of the times 2, we actually have to think of it as a compression by 1/2. So it's inverse of what we see. When we have the equation. Inverse of what we see when we have the equation. So I see a divide by 3, so I stretch it by 3, increasing. Here I see a times 2, so I'm going to compress it by 1/2. All right, so what happens to each point? So, for example, this x, what's it become? So take a look at this first point, -6, 2, and tell your neighbor, what does this point, where does it stretch to go? All right, so this one has to be cut in half. So all of these are being cut in half, and all of these are being tripled. So -3, and this becomes a 6. So mentally, we can do all these. This whole row gets cut in half, a column, and this whole column gets tripled. So we end up with this scenario. I do want to point out again that whenever we have intercepts, this intercept here and this intercept here, it's still going to be an intercept. It just slides along the axis in some way. This one gets compressed inward. This one gets stretched downward. So those two images are still on the axis because of the nature of multiplying by 0 there. Let's look at example 3a and call it a day. The line 41x minus 29y equals 700 contains the point 39, 31, and 10, -10. Use this information to obtain 2 points on the line with the equation this. So notice something here. Take a look at each of the x and the y there. What is changing? Come up with a rule, and then apply that rule to each point. So what's happening to the x? It's as if we're doing this, right? It's as if we're doing that. Why? If you cut the coefficient in half, which is the same as dividing the x by half, or by 2, that's effectively what's happening. Next, what's happening to this one here? Minus. So the original is 29. How do I get to an 87 from there? If I were to triple that, essentially, this is what's happening. So how do I describe, notice this part is the equation. So how do I describe the rule? What is happening to the x? What's happening to the y?
Fraction, which is division.
Good. So here we see that the x is being cut in half. So in the equation, so the rule means I'm stretching it by 2. I'm doubling the x. Here I see in the equation, my y is being tripled. So that means I'm compressing it. The vertical is being compressed by 1/3. So that's my rule. So all I have to do now is double my x and divide by 3 on my y. Double my x, divide by 3 on my y. Double my x, divide by 3 on my y. So this one here is going to become, so double the x to get 78 and divide by 3 on the y to get 31/3. Sir, not perfect, not clean numbers that we always like, but that's okay. This one here, double the x to get 20 and divide by 3 to get -3 1/3 or -10 thirds.